couple of really important things on Learning Suite. First of all, there have been some emails sent through Learning Suite where students have asked questions and I've been responding. So make sure that you are checking or forwarding the Learning Suite emails to where you can find them. Okay. Second of all, if you come under Content and then tap on Course Materials, you will see Exam Preparation Materials. This Unit 1 review sheet, if you look at this, there are 40 items. These are the 40 need-to-know items for the exam. Okay, so this is what you're going to be worrying about if you know these things from all of the fun things that we've been learning. Okay. This second item included on Exam 1 shows you the material that will be provided during Exam 1. It's just the last page of my test. So you will have these different equations and the definitions of the variables. So you need to know how to use them. The speed of sound in air, it's here both in meters per second and centimeters per second. And then this table that had to do with the absorption coefficients. So these things are available. These are the things you do not need to memorize. Okay? Just need to know to look for. So I'm going to go ahead and work through the examples that were given in class. Okay. Oh, just one more thing. Again, to check your Learning Suite emails because Kayla Snar, RTA, is going to have a Zoom office hour tonight. And then Caleb has some in-person office hours. These are 4 to 6 p.m. tonight. And Kayla's 6:30, 7:30. So if you have any questions about those or can't find the answers, please email Caleb or Kayla, RTA. Okay. All right. So I'm going to be flipping back and forth here between the review sheet and my little writing here that I get to do. Okay. So on the review sheet, the first things that we talked about in class were actually at the end of the review sheet. Okay. So questions number 40, and 38, 37, 36, 37, 39, 40. Okay, and at this point, what I did, I'm going to send this over to my Notability so it's a little easier to get to and I can write on. Spot so I can find it. For these questions in particular, but for all of the questions here under slides, again, content, course material slides under Unit 1, you can find PDFs of slides that have tons of information in them. So particularly for this Unit 1.12, if you go to this file and you go to the review, this is related to question number 26. What are the kinds of signals at these different places? And there, that's in the previous one that actually has the answers. You come all the way to the end. This talks about, so this here is basically telling you if you want high or low bandwidth, dynamic range, signal to noise ratio, efficiency, those should be high, distortion should be low, and dispersion is on there. We don't talk about how much it should be high. This is where you get the answers. Question number 38 is about frequency response curves, which look like this. We have frequency on the horizontal axis and response on the vertical axis. The frequency response is just how the transducer, the loudspeaker, the radio, or amplifier, or whatever, how it treats the different frequencies relative to each other. So 0, or roughly 0, plus or minus 3 dB, is the area where we say it has a flat response, like that's the frequencies that the transducer is designed to be used at. So on this picture, I would say the bandwidth for the flat response area is from 125 to 4,000 hertz. It's just kind of plus or minus. feature at 62 hertz, so if it's ever a large spike, the positive on the response curve, that is a resonance. That's some frequency that gets amplified by the transducer because of the natural standing wave, natural frequency. Okay. And the bandwidth again would be flat response, which would be 125 to 4,000 hertz. And then the above 4,000 part there is the which is response. It's just not able to produce those frequencies. That's what. With regards to number 36, which was the last other one we talked about in class. So, one of these where we first talked about transducers, that diagram is in there and has all of the things actually labeled. I'll tell you here, but you can find it actually written down. And so, point one, the input to the tape deck is magnetic, so magnetic information encoded on the tapes. The input to the CD compact disc player is optical because there's a little laser there. So eye-based that is actually reading the divots and grooves. And then the radio tuner is an electromagnetic wave. Radio waves, infrared, visible light, ultraviolet, gamma rays, all of those things. Okay, points 4, 5, and 6 all have electrical signals traveling through them because these components are all connected with wires. You can see them traveling through electrical system. And then the output from the loudspeakers is acoustical signal. The sound is exactly they're being changed and modified as they go through this change. So please consult those slides to be filling those. So if I look here, the next set that we talked about in class that are really good to think about are here questions 8 through 21. This idea of standing waves on a string or in the tube, the air in the tube from the sun. And so I'm going to talk through each of those now. So number 18 is the one about indications. So what kind of indications should we have? We have fixed ends of strings. And then we have free ends of strings, like and like that. And if you are doing a repeatable standing wave pattern with a natural frequency, the fixed end of the string will have a displacement node, meaning that the departure from equilibrium is 0. It's just standing. And the free end of strings will be a displacement antinode that goes to the largest displacement. We tend to draw these things kind of like this, right? And then there's some zero line, and at one instant in time it's there, and then it, let's see if I get this done. Okay. And then this is our equilibrium line, and then it's basically oscillating between that and something like this. Okay. So these are going up, down, up, down. And the node points are the points that don't move. So think about shaking a jump rope in these patterns we watched. That's different channels with those. So the dots are the nodes. Okay. And then where I'm putting the X's, they're antinodes at those positions. And it's going back and forth, back and forth. Okay. So for number 18, if there are nodes at both ends, then this would be an example of a fixed string. if there is a node at one end, but again, an antinode at the other, okay. Let's go like that. Then the nodes again are the points that stay still, and then the antinodes are here. Okay, this is again, I'm drawing it this way to show it's vibrating or oscillating between those two. Okay, so here this would be an example of a fixed free string. Now, the thing that's interesting is that open ends of tubes have a pressure node, and closed end of tubes have a pressure antinode. So if I had these same pictures, whatever has nodes at both ends, that could be a fixed string. It also could be an open tube. And the fixed free string could be an open closed tube. Their pictures and the math behind finding the frequencies and all of that are identical. Okay, so that's good to remember. So now the question is, what are the natural frequencies of those cases? So this gets into number 19 and half of 20. So again, this is for the fixed string case and also for the open tube. So you have some length L of your string. Okay. Mode 1, gonna look like that. This is your equilibrium, and it's going back and forth, and it has one antinode. Mode 2 will look like that. And then mode 3, try again, will look like that. Okay. So you can see the nodes and the antinodes. The number of antinodes is the mode number. We would call this mode 1, and this mode 2, and this mode 3. Okay, so these are the modes, the standing wave patterns for the fixed string and the open tube. Now, for the natural frequencies of these modes, for these cases, the fundamental or first natural frequency is F1, and that is V over 2L. Okay, that comes because half of a wavelength fits on this string. The natural frequency for all of the higher ones, for the fixed string or open tube, is a number n times F1, where n is equal to 2, 3, 4, 5, everything on it. Okay, so those we call integers. They're basically whole numbers. So the fixed string and the open tube have all the harmonics, meaning all the integer multiples. These equations you do need to memorize. They are not on your sheet. Okay, so that's the first part of number 20 as well as number 19. Okay, and then for number 21, it's talking about, well, the open tube, but then also the open closed, still number 20. The open closed tube. What do those pictures look like? They have to have a node at one end and an antinode at the other end. This is a shorter string because it's easier for me. So that would be mode 1. This one would be mode 2. This one would be mode 3. Something like that. Okay. The horizontal line is the equilibrium position. And then this dotted line is it's going back and forth between those. Up and down, up and down. Okay, for this open closed tube, because only a quarter of a wavelength fits on the string of length L, or sorry, in a tube of length L, F1 for this case is V divided by 4L. And then here, 3/4 fits of a wavelength, and then 5/4 fits. And so for this one, F2 is 3F1, and F3 is 5F1. So for this case, you have only the odd harmonics, only odd numbers times the fundamental. Okay. All right, so that is number 20. Number 21 then is talking about lists of frequencies. Okay, so if I had frequency list that was like 25, 75, 100, 150, 175, or something like that. And the question is, are those harmonic or not harmonic partials? Okay, they are harmonic partials. Because any frequency divided by the first one gives you a number without any decimal places, okay, an integer. So you would just take the numbers and divide by whatever's lowest, okay, and then you would see, oh, yep, those are all, in fact, just integers, whole numbers, okay? So whatever your list is, you can tell. A list that maybe was 25, 37, 75, 81, we'll do 75 for right now. So 65, 81, 122, something like that. Hertz, it should be hertz. Okay, those would be inharmonic partials. Because if you do 37 divided by 21, you get a fraction. Anything with a decimal place is an inharmonic partial, okay? So that would be a list of inharmonic partials. Now, if you have something that is something like this, where you maybe have some frequencies that are multiples and some that are not, okay, then you would say that there are some harmonic, the 75 and the 100, and some inharmonic. Okay. And then you might have some that, I don't think it is in this list, we'll get to it more later, but if it's like 75, 51, 74, 101, you know, that they're almost integer multiples, then those would be almost harmonic or slightly inharmonic. But again, I don't think that's on this test. We'll get to that more with musical instruments. Okay. If instead of a list, you are given a picture of a spectrum, okay, just remember that the tick marks are evenly spaced. Okay. So if we had, you know, something like that, where there are not evenly spaced, right? If they're not the same distance as that, that would be an example of inharmonic partials. It's a function of frequency and amplitude. Whereas if you had something like that, would be harmonic partials. It doesn't have to have every single one. The question is just, are the upper ones integer multiples of the bottom one? All right, now we're going to, the next one we did in class was the Doppler shift one. Here, number 16, and then we will be doing number 14, the echo. Okay, so number 16, Doppler shift. So for the Doppler shift, we're talking about a shift, the perceived frequency changes when something is moving towards or away from you. So you'll have your original frequency, and then you'll have plus and minus some shift, which we call delta F. And that shift, delta F,
is this equation, this shift equation is on the review sheet, is the speed of the object over, or the observer over the speed of sound in air, the 340 meters a second, times the original frequency. So for example, if we had an original frequency of 2000 hertz and something was moving 1.7 meters per second, then the shift would be 1.7 meters per second divided by 340 meters per second speed of sound in air times 2000 hertz. If you multiply that out, I think you get 10 hertz. You would take that shift up here and you would say 2000 hertz plus, because that was given down here in the problem, plus or minus the shift. So that plus or minus 10 hertz. And then you would have to decide, am I doing plus or am I doing minus based on your own physical experience. If it's coming towards you, you know the perceived pitch goes up. You would use the plus to get 2010 hertz. And if it's going away, then you would use the minus sign and you would get 1990 hertz. Okay, so that's the example with the Doppler shift. Okay. The next one, now I think it was 14, is about echoes. And the idea with the echoes is you're standing here listening or whatever, you make a loud sound, and then the sound has to travel to the wall and back. Okay, so if this is the distance to the wall, then the total distance that it travels is twice that. So that's the key to remember. The equation that is on your exam is V is d over t, which is that the speed is equal to the distance divided by time. This is just a general true equation for any kind of motion. But for us, we're going to be saying the speed of sound in air, okay, is the distance over the time. Now, the trick is that if you use just the distance to the wall, the time you're talking about is only the time to get there. If you're doing the time for the echo to be heard, then you're doing the distance to the wall and back. So you have to, one way or the other, just keep track of that extra factor or two. All right. So I think those are the primary ones. Let me see. This was my, so I have number, okay. So the one other one we talked about in class was number 5. Number 5 says, when given the natural frequency of a simple vibrator, like a mass spring system, calculate the driving frequency that will cause the vibrator to achieve its greatest amplitude. So this is the idea of resonance, and that when the driving frequency is equal to the natural frequency, you will get the largest amplitude. So it's very simple question, so don't make it any harder than it needs to be. You just want the driving frequency to equal the natural frequency. That's the actual description of resonance. Okay, so like I said at the beginning, please make sure that you're using the resources on Learning Suite to your best of your ability. We have the unit slides here. We have the exam preparation materials with the review sheet, and this info included on exam 1 is where you find the equations, okay, that are on the back. A good way to recall and practice for the test is to look over your old homeworks, or you can take blank copies of the handouts and try to answer the questions from your mind, or after you filled it in once, you could just take another example of the review sheet and then just write out the answer. So recall is better studying habit than just reading over your notes. Okay, good luck with the exam. Please let myself or one of the TAs know if you have additional questions. Good luck.